Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about district cooling. So let's dive deep into it. So yes, I have covered district cooling, but never as a dedicated topic. That's why I'm covering this. So just to overview, what exactly is the problem that we need this puppy? Well, our demand for cooling is growing and is growing exponentially. And we need even more. Meaning back in the old days, 100 ton of cooling was like, whoa, sold in one day. Now we have 10,000 ton of cooling sold per day. So our demand is growing exponentially, and Indians were kind of behind the schedule. And again, let that be very clear, that applies to all other places also. We just like, we should have been better at this. It's just that hundreds of small units do not work. Meaning, let's just say if you have an apartment complex, every Tom, Dick and Harry starts to install their own small AC, which is very common in Vietnam, basically Asia specific place. It's a bad idea. Like, it's not bad, it's like, it's deadly bad. So we really have to learn that we cannot do this. Like, that is like a no-go. And again, you can see the results from 2001 to 2021. We basically are frying all these metropolitan in India. And again, same is true with China, same is true with Vietnam, same is true, basically this whole region, that is true. And let that be very clear, this is same applies in American places also. Like, there also have similar type of heat map. So we have learned this the hard way. We cannot have hundreds of small units. We have to use one larger one. And there is serious risk of feedback loop, meaning you're like, okay, I have a building. Let's just say you have a good insulation. What does that mean? That simply means if you're maintaining 25 degrees Celsius inside, which is a normal-ish temperature, and you have the outside temperature 35 degrees Celsius, that outside your insulation is like, nah, bro. The heat leak from 35 degrees Celsius to 25 degrees Celsius is very slow. It's almost negligible. It's like, yeah, you know, your AC does have some partial load because of that, but it's not end of the world. Your AC is like, I got this. But now imagine that is 45 degrees Celsius. Your insulation is like, whoa, man, we can't handle this. And now imagine India, 50 degrees Celsius. Yeah, the wall is like, no, the wall starts to act as a heater. And at that point in time, air condition reaches a point where it's like, yeah, man, I can't do much in this. So that creates a scenario. And assuming, let's just say you're like, what if I put really powerful air condition? Here's another problem. Once you leach the heat from the inside environment and dump in outside air is not magic. That be very clear. Outside air is not a perfect conductor. It will not just take the heat and dissipate instantaneously. Air is a very poor conductor. Penalty of that is, because it's a sparse molecule, it takes times to bounce around and all that. And to create a convection, unless you are talking about a boom device, the convection currents are very slow. Of course, you can see it, but it requires very high heat to actually be that effective. So here, when you are talking about kind of low T delta, basically, let's say outside environment is 50 degrees Celsius, you made it 55 degrees Celsius. Yeah, the convection is not gonna be like cool down. It's gonna be like trapped there. And it's really bad if you have like large tall buildings. And if you're surrounded by large tall buildings, yeah, then you have a whole dead space where heat is just piling up in daytime. So that creates a scenario. Now your walls are like, instead of handling 50 degree of supposed temperature, they are trying to hold back heat of 55 degrees Celsius. Yeah, that's not gonna work. That fundamentally creates a feedback loop, what we call more demand equals more heat output equals even more demand, which is again unsustainable. And if we do not solve it, we'll reach hell very quickly. So let that be very clear. Other places will also reach it, but India will reach it kind of soon. Vietnam will soon. And again, some places in China is like, it's getting hot. Like Indians, I'm saying that, it's getting hot. So there is a serious problem. We have to solve these things. There is no hee ha, we have to solve this. So what's the logic? Why district cooling actually solves the problem? Well, it solves the problem simply because it utilizes what we call economy of scale. As we all know, like if you try to manufacture like, one thing versus hundreds of thing, it's a very different game. And same goes with the air condition, but in reverse direction. For example, if you want to have apartment complex and hundreds of people are utilizing 1 ton AC or 1.5 ton, let's just say if they have that many, how many bearings they have? Just count the bearings. You will have a lot of bearing surfaces. Now compare that to a centralized chiller. Now that chiller could literally be like this. This is a LG chiller unit. This puppy has a floating rotor, so to say. And again, many systems have magnetic bearings. They do not even touch. There is no bearings. There is no frictional losses. Now you're like, does that matter? Yes, when you are talking about 100 ton, it matters. When you're talking 500 ton, that matters. So 1% of a very large number is huge. So that's why you get the benefit of economy of scale. Another aspect is, when you build a building, is designed to do one damn thing. Like whenever you are building another thing, let's say that blue office building, that's an office building. It has to look good. It has to have parking. It has to be like this and that. Like it's a building first. This puppy with a district cooling, it's a cooler first, meaning the engineer gets a blank canvas. It's like, okay, design does not matter. Make sure it cools well, then we're gonna figure the other things out. So that gives you much more better airflow path. Like you can see all the sides are easily open. It's just like easy come in, easy go up, don't worry about it. So, and why would buildings, like right now buildings would do that? Well, they get a lot of savings. They get savings in two whole point. First, the volume savings, meaning how much area they have to have, as we call mechanical room, that disappears. You can just have a small heat exchanger there. Not small, but much more simpler. And the electrical loading goes down. So your electrical bill goes down. The space, because again, buildings are fixed, you have this fixed amount of plot. So the amount of space that you get back is significant, which you can utilize depending on your requirement. You can be like, hey, we can have underground parking. We can have far more floors, because many of the building top floors are preoccupied, so to say. You can't do much there. It's just cooling towers there, like this sort of structure. So instead of having like this, you could have a restaurant, you could have like, a space, or you can just utilize it. So there is a genuine benefit for building owners where it's like, hey, let me not worry about cooling. I want to utilize this plot of land for basically profitizing. So you're like, okay, you focus on that. And this building is like, I'm only going to focus on chilling. So it works. And what kind of gain we are talking about, right? I'm giving you an idea like hundreds of small unit versus one big unit. What kind of energy gains we are doing? Now let us be very clear. This is ancient technology. We have been using this. And the reality is bare minimum. Like if you did not do your maths, you will get 10% savings, which again, talking over city level scape, that's magnificently huge. And if you are like properly designing from day one, that's up to 50% of energy saving. That's shut up, take money. That is, shut up, take money. And why it's that big? Well, simply because you have hundreds of phantom loads. For example, bearing itself is one thing. Another is if you have to distribute electrical load, same amount, let's just say 50 megawatts, not 52 slow, 500 megawatts. And if you have to distribute it every building, like, I have 500 megawatt, now you have 1 kilowatt unit here, 1 kilowatt unit, which is average air conditioner, one, versus one big unit. One big unit, you will have a direct high voltage line that is like, let's say 135 kV, one step down, one big load, done. Versus whole grid heating up simply because everybody is leaching little bit here. So that has a magnificent difference, and just the parasitic losses goes down. So there are many other things like that, specifically the fact that you can design a system which focuses on airflow, focuses on convection, optimizing the convection. So all those things pile up. And again, even refrigerant, for example, it would be unwise for a company to invest into ammonia refrigerant, because again, it's a toxic thing. It's the best thing, but it's a toxic thing. But if you have a dedicated building, you could have dedicated terrain stuff, exactly like how we deal with substations. Electric substations are not a laughing matter, but you have to deal with it. So you deal with it. So here you can have that benefit also, meaning use the best refrigerant possible known to humanity, ammonia. It's a good for environment, basically completely natural because it's made by nature, and it gives you very high COP. So it's a really cost effective. It compounds on itself. And what are the benefits that public will get? Public will get lower water usage, meaning those buildings, instead of drinking water, they're like, hey, we just pay someone and we get cooling. We do not have to boil water away. So that's awesome. And grid, that's another benefit. The daytime overload, which again happens everywhere, every country, that goes down. Because these things can shift load, meaning they're like, hey, daytime, I'm not even going to turn on. I'm going to use my energy storage. I will explain that further. But the idea is during that peak loading where transformers are like hanging on to dear life, they're like, nah, bro, chill, bro. Be good. Chill. Don't worry about it. So there are multiple benefits for whole civilian population, and reduces heat island effect, because again, hundreds of small one, that if you're saving that much energy, fundamentally you have the benefit, and you are not getting trapped by air thing, because generally they are put in such a way that you have a large enough empty space so that convection can be done properly. So you do reduce it. Now again, let that be very clear. It does not eliminate it. It just reduces it, which again, letting it free run, I should reduce it. And runaway can be stopped. Basically, you will not eliminate it, but you can stop like that vicious cycle. And especially if you want to do daytime shifting, meaning you do not run air conditions on daytime, you run it at night. And that way you have the benefit. You let the daytime heat is absorbed, you dump only at night. You do not create compounding effects. All of this is possible, have been done simply because it works. It's a time tested thing. It's just that how much, 10% or 50%? So how do you construct something like this? It's a very simple point. You build a dedicated building for cooling. Everything is designed for cooling first. And then you have multiple massive chiller units, because while we are talking about 500-ton single unit, that's not that big. When you're talking about district cooling, you are talking about 50,000 ton, 1 million tons. I'm not even exaggerating. There are many systems in Kuwait, Singapore, things of this nature that have like way too many zeros to count. So you are talking about like multiple ginormous chiller units. And how do you transmit that much cooling? Well, you utilize ancient technology of insulated pipes. So what sort of temperature we are talking about? You're generally trying to use as much pure water as possible, distilled pure water, and you do not want to go to 0 degrees Celsius, because again, there is a very risk of freezing and clogging the system. So you generally keep it at 4 degrees Celsius or 5 degrees Celsius. That's your sweet spot. And if you are in Western Hemisphere where temperature can drop, you may want to add antifreeze penalty. It will reduce your thermal capacity, but it will make it far more resilient to if, like, let's say they went through a cold spot, it's like it won't freeze and clog the system. In India, we do not worry about that. We don't. Even if we try to freeze it, Indian atmosphere is like, nah, bro, what are you trying? So we cool. We just use raw water, as in distilled water, to around 4 degrees Celsius to 14 degrees Celsius. So you send cooled water, that is 4 degrees Celsius, you expect return to be at 14. Let that be very clear. Most systems are designed for 10 degree T delta or 9 degree T delta, and that has to be maintained. Basically, they will penalize you if your hotel's heat exchanger is not giving that. So that you do. And then you have plate heat exchanger for the customer end. You have chiller units at your cooling building, but your customers get basically plate heat exchanger. Now, why plate heat exchanger? Generally, they are simple, very high efficiency, and super easy to scale. Meaning, let's say a district unit is being built, they will commission a master design. It's like, this is the template. Okay, cool. Now, let's say, what if you have a lot of load? It's like, okay, da, 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 da. And it's like, no, this building has low load. Da, 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 da. Nothing more than that. It's super easy. One design, so you can have parts, supplier, stocks, everything, and you can just scale it based on demand. And that's how we do it. So plate heat exchanger, customer gets it. Now, how does customer do the cooling? Okay, they have a block that can get cold. What do you do with that? You run your coolant through it, which again could be distilled water, could be distilled water with antifreeze, or could be oil also. But I've never seen anybody using oil, because why would you? It's a lower thermal capacity. And then you send that cold fluid through what we call air handling units. Most large buildings have that, and that's how you get your cooling. Or you can send it through air conditioning, which again not recommended, but it can be done. If you really want very low temperature, you can do that. Like, let's say you have vaccination storage. In those sort of scenario, like, yeah, it would be better if I, instead of dumping the heat into ambient air, dumped heat into a cold liquid that is, let's say, 5 degrees Celsius or 6 degrees Celsius, because again, those ultra low temperature vaccination cabinet requires minus 80 degrees Celsius. So helping them is matters. But again, you do have to talk with the district. It's like, hey, you cool with this? And so that's the plate heat exchanger part. You get the cold liquid, you circulate it via either fan coil unit or air handling unit, you get your cooling. After that, how do you get billed? And again, this is not fixed billing. It's not like, okay, you have the system, once per month you get this amount of price. No, it has to be measured based on your requirement. So to do that, we utilize BTU meter. Do not ask me why we are still using British thermal units of measurement, even though most systems actually use kilowatt, but it is what it is. So you require three primary things. First, you need a control valve that actually allows you to control. Second, you need two thermal sensors. So basically you measure how much is going in. So going in part, basically things that are coming to you would be always at 4 or 5 degrees Celsius. And the out part should be at 10 degree up. Now, how does the system maintain it? System controls the flow. For example, you are dumping very little amount of heat into the system. Let's say there is not load in your building. You are dumping very little heat. But again, the temperature will not go to 10 degrees Celsius. So computer will detect it. Computer is like, okay, let's choke the flow. It will start to slow down the flow, and until it reaches 10 degrees Celsius, it will try to keep it as stable as possible. Now, let's say it opened the max flow, and then you are dumping so much heat into it that outside is like, yeah, I'm return water, instead of being 15 degrees Celsius, it's at 18 degrees or 20 degrees Celsius. They're like, yeah, they're gonna call you up. It's like, bro, something is wrong. Either your heat exchanger is not up to the scale, or you're overloading it too much. Now, generally, it simply means it's not perfect for that size. For example, let's say you design the building expecting 100 megawatt of heat load, and turns out you are dumping 200 megawatt of heat load. They're like, yeah, please increase your plate heat exchanger size. So that's how they do that. And again, all computer systems try to do is maintain T delta of 10 degrees Celsius. So nothing fancy or complicated. It's just you have a building that is built for chilling. You have pipes which are insulated pipes. You have input and output, and then you have plate heat exchangers, and then you have a measurement unit which just temperature sensors and flow sensor. Nothing magical or complicated, and a control valve that does the actual control. And then you bill them based on how much energy they consumed. And target is optimization at 10 degrees Celsius. Now let them forget that 10 is flexible. If the system was designed for 8 degree T delta, they will focus on 8 degree. If it's designed for 15 degree T delta, they will focus on 15. And generally most of the time the coolant temperature is low enough that it can do dehumidification, it can do cooling, it can even do act as a like a refrigerator. Like 8 degrees Celsius is cold enough for refrigeration. Many things can be refrigerator. So that's the whole point of it. It's a very useful, and you do not have to have your own chiller. You do not have to have your own cooling tower. You do not have to worry about those things. And most district systems have double redundancy or triple redundancy, meaning likelihood of those puppies failing would be low, very low. Now, those are the core fundamentals. You will always have them. What can we add to it to improve it? Well, the first thing is energy storage. Now, when we are talking about energy storage, in this context, we are talking about thermal energy, not electricity. Let that be very clear. We are not talking about electricity. So when I'm saying it's offsetting the peak, it's not that it's charging a battery during downtime. It's charging a thermal battery during the downtime. So energy storage for load balancing, and load balancing is very critical here, because if you directly add it up, okay, this building has this much required, this building, the number would be too huge. Like it would be too huge. So what do? We generally try to match it as closely as possible, and then we have a buffer. Now buffer allows us to, like, that spiky things is like, chill bro, chill. And again, benefit is of having water is that it is also a very good low pass filter. It just chills out everything. It's like, bro, chill. So for load balancing. Now, India's Gujarat system, that is first of its kind, it utilizes a chill water tank. Now, like, okay, that sounds simple. It is very simple. It's just a tank, insulated, large volume of water, as large as you can make it, and it keeps the water as cold as the mean coolant temperature. So let's say 4 degrees Celsius. So that works. Super simple, super easy, effective, no problem. Then you have its bigger brother, which is ice storage. Now, ice storage allows you to achieve even lower temperatures. For example, if you really want to cool some hot puppies, you want a T delta to be low. So in this scenario, you are talking about 0 degree, because again, if you know water melting, it always goes to 0 degrees Celsius. If you have ice melting, 0. That would be the temperature. So it gives you lower temperature. Rather than 4 or 3 degrees Celsius, you go almost 0 degrees Celsius. Now liquid would be 0 degrees Celsius, and liquid, it's a very good conductor. So benefit is actually you get almost 1 degree Celsius of coolant temperature. Really good. Capacity. Now this is where this puppy shines. The capacity is monstrous, meaning if I give you 100 kiloliter of tank capacity, how much energy can be stored in ice versus how much in liquid water? It's not even a competition. Like this would be chilled water would be like 1 hour of chilling time. Ice would be like, like Chicago uses it. It's like, I do not turn my air condition during daytime. So like, when do they turn it on? The moment sun goes below the horizon, local time. So sun goes below horizon, air conditioners like, I got this. This is my time to shine. It starts. Now, then why don't everybody use as ice battery? It does require a lower temperature, because you have to understand ice has this weird property known as insulation. So basically you have a pipe, right? And you're running refrigerant through it. Refrigerant is like, let's say 18 degrees Celsius, minus 18 degrees Celsius. You're like, okay, everything will freeze. No. Only a thick, basically a thin ice layer would be formed, and then it will slowly start to that's why ice takes so long to make. It's not the energy part. We can leach that much energy, no problem. It just takes so long to transmit the energy through ice. So you have liquid, super good conductor. You have an ice layer, super bad insulator, as in like good insulator, but it makes your life harder. So that takes a lot of compressor load, meaning if you want to do this ice system, your chiller units, basically the compressor parts, those will be like, yeah, it's a bit of a stress load. Then why do Chicago do that? Again, they basically do not turn on their air conditioning units during daytime. It's only once the sun goes down, the earth starts to cool down. It's like, okay, now they start to run. They run it overnight, completely freeze up everything up. During daytime, it melts. And again, there 1 million unit, 1 million liter kind of units we are talking about. It's a massive unit. And those things are your energy buffer part. Okay, another thing is, if you have a power plant, for example, if I want to do this in Delhi has a lot of jet engine power plants. They have bonkers amount of waste heat, and many other places have coal power plants, which again has bonkers amount of waste heat. So if a power plant has a rating of, let's say, 1 gigawatt, just assume it has 2 gigawatts of waste heat. So that's a lot of waste heat. Like, that's not a little waste heat, that's bonkersly large amount of waste heat. It's like, what if you run air condition on that heat? Now, thankfully, we have this ancient technology. Before we had compressors, we had this technology. We call it absorption chiller. Now, absorption chiller, we run on that waste heat, and then we're like, okay, if we can cool something down using the waste heat, then why don't we do it? Well, we do it. All big units have that. And generally, why we don't use fire to make a refrigeration is simply because the COP is very poor. For example, absorption chiller, you dump 2 gigawatts of waste heat. If you are lucky, you're going to get a 900 megawatts of cooling. Now, compare that to electrical energy, compressor would be like, bruh, I can give you COP of 3 on a bad day, COP of 5 on a good day. So it's non-comparable. That's why we do not, burn fuel to do refrigeration. We used to, but electricity became cheaper. So, but again, when you are talking about a power plant, you have waste heat. You do not have to worry about it. You can just utilize that waste heat. And in those sort of scenario, let's just say your district cooling requirement was, let's say, 1 gigawatt, and you are only getting 900 megawatts. You'll be like, okay, I'm going to put 200 megawatts of electrical chillers just to buffer things out. So it does work. It's what we call combined heat and power system, or combined heating and cooling systems. So that's work. And you can utilize the waste heat, because again, you are moving heat from one place to another. You can utilize that for other things. That depends on you. There are some places who utilize those sort of heat for some industrial process where they have to dry off materials, raw materials. You can go YOLO on that. You should write down in comments if you know any places where you can utilize low degree heat, because there is a lot of heat. Like, while the T delta is poor, the heat amount is bonkers. Like, you are talking megawatts, hundreds of megawatt to gigawatts of waste heat. So that's a lot of energy. Please don't say creating electricity. The best option you have for that is what we call organic Rankine cycle. It's just using a refrigerant instead of water and steam. And it does work. It's a known thing. It's just poor. It's like, if you are lucky, like I'm stretching that luck part. If you're lucky, you're going to get 5% of conversion efficiency. So yeah, the machine will cost more than the electricity. Basically, you'll be like, yeah, I can just buy solar panel and get more electricity than that. So that's why people don't do it. You can get it. It's just like, it's not worth the machine that it will cost. And again, T delta is too poor. Sometimes they have used with a diesel generator power plants where they have enough high temperature waste heat, but yeah. So there are add-ons. Energy storage is first thing. Utilizing waste heat is another thing. And you can utilize the reject heat also if you have a certain requirement, which again, that's why I was talking about that coastal cities. Coastal city can utilize that waste heat to get water, utilizing low temperature thermal desalination. So what can we expect in the future? Now, future part is Earth is heating up. Now, let that be very clear. We have to improve our cooling, or we're gonna poof, like flat out, poof. Because this puppy, like your lungs, has an upper limit. Basically, how much hot air can go inside. There is a point where it will be like, yeah, I'm mediated. So fundamentally, there is upper limit, and there is a even dangerous limit, what we call wet bulb temperature. Now, again, it may not be that big of an issue to people who are very close to poles, but it is a horrifying issue for basically Vietnam, China, India, things of the same. Basically, majority of Earth's population, because your body dumps heat via evaporation, and if there is already humidity in air and temperature is already high enough, you will be cooked. Basically, I'm not even joking. No, it's not like, oh la la. No, thousands of people are starting to die annually because these sort of heat events are, instead of happening once 100 years, it's happening almost yearly. And if our global temperature starts to keep going up, yeah, that will, instead of happening, once or twice, it will be like, this is the whole summer month. Basically, the big cities would be so cooked, they will no longer have any poor people. They will be just poofed. And not even joking, like not hee ha. No, that's how deadly it is. And we may have only till 2020 to fix these things. If we do not, yeesh, bad things. So district cooling will become a necessity. I'm like kind of shocked that India took so long, but at least somebody started somewhere. Better than nothing. And again, I have to say, a lot of Middle Eastern countries, they were surprisingly good in this. They jumped into this. I'm like, just jump into low temperature thermal desalination. That will be wabi. Like, you do not have basically brine pollution of the ocean, and you will also get energy efficiency. So win-win-win scenario. So that is something we have learned the hard way, that normal small air conditioning units does not work. We have to go to centralized system. And reducing power draw is key. That's why we want to utilize the waste heat also, because if you can do work with waste heat, why throw that heat away? Like, that's the core point of it. Do not throw basically waste heat away. Do figure out something with it. Like, if you can utilize it, go YOLO on it. And combined heat and power is the key, because again, even though we could even in future, like let's just say India goes YOLO on solar, and solar does take care of all our electrical needs, we can utilize basically PVT panels, basically photovoltaic thermal panels. Basically, we run hot water behind it, and that heat can be utilized to run a very low efficiency. But again, better than waste heat. We can run an absorption chiller, and again, that will work with conjunction with basically normal chiller units to basically bring down temperature low. So there is a lot of potential in the future where we can still have a growing, thriving city without cooking it off. That's what I call tri-generation. You take your fuel to rotation conversion, generator gives you most of the power, then you send it to absorption chiller, that gives you cooling, and then you have hot water. Now, I used to worry about like what the hell Indians were gonna do with hot water. Then I realized washing machines also need hot water, and then I realized, which we are kind of behind in this technology, is that dishwasher requires very hot water, 80 degrees Celsius kind of hot water. We good. Clothes drying can easily enjoy hot water. Basically, you have a radiator that has hot water running through it in a sealed chamber, and voila, perfect clothes drying without any issue. JJ. So even on daily use case scenario, we have more than enough demand for hot water. So that actually utilizes reject heat for that. So you will reduce total overall load of a city so much that it will become stay livable for longer. So this is a good technology. Thankfully, nothing magical required. And again, plate heat exchanger. How wide you want? Nothing more than that. So this was my presentation on district cooling specifically. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.